Alright, this is the fourth video for the mechanics unit notes. And for this one, we're going to talk about mechanical advantage. Now, a machine is a mechanical device that makes it possible to do work more conveniently. It increases the speed of an operation or decreases the force that must be supplied by changing the direction of the force. So let's take a look at a bicycle. In a bicycle, we have an input and an output. And one way we have of calculating the mechanical advantage is by taking a look at the input distance divided by the output distance. One of the things we would want to do then is, looking at this, we would see that our input distance is 15 centimeters and our output distance would be 34 centimeters. Now, something else that's very, very important to notice, machines do not reduce the amount of work you do. The input work will always equal the output work. So let's figure this out here. So let's figure out the input work we're doing. So remember, work is a force that's parallel to a distance. So here, the work that I'm putting into the machine. Well, the force I'm putting in is 1,000 newtons. And the distance I'm covering is 0.15 meters. So that equals 150 joules of work. That's how much work I'm putting into the machine. Here's my output work. So I have 440 newtons times 0.34 meters. That equals 149.6 joules. So we see that it's a little less, but it's only 4/10 of a joule less. So it's practically the same. Now, for mechanical advantage, what we want to do is we want to find the output force divided by the input force. So for our bike example up here, it would be 440 newtons divided by 1,000 newtons. And when we calculate that, we get 0.44. Now notice it's unitless. Okay, there's no units. This is a ratio. Another way of doing this is by taking the input distance divided by the output distance, but we can take a look at that later. Now, torque itself is a rotational equivalent of force. So we can write the mechanical advantage for torque like this as well. So mechanical advantage can also equal the output torque divided by the input torque. And that can be very helpful when we go to do some calculations with torque. All right, something else to remember, the number of teeth on a gear can help us calculate mechanical advantage, where we have the output divided by the input. So for this first one, this non-compound gear, let's say that this side is the input and that side is the output. What I would have is I would have 36 divided by 12 times 60 over 36, which that just equals 5. If the mechanical advantage is greater than 1, it's set up for torque and you sacrifice speed. If the mechanical advantage is less than 1, it's set up for speed and you sacrifice torque. All right, let's take a look at this example. This is a compound. So the mechanical advantage would equal 60 divided by 12 times 60 divided by 12. That equals 25. So we see a much, much bigger gear uh, increase for this. Now, once we have the mechanical advantage, we can use that to calculate rotational speed. So what this means is that the input rotational speed, omega n, multiplied by your mechanical advantage. Actually, I got this backwards here. The output speed equals the input speed divided by your mechanical advantage. So in our examples above, the motors turn at 100 RPMs. So if I divide that by 25, I get 4 RPMs. Now, in a previous example I just showed you, we saw that the output work was less than the input work. That comes down to efficiency. In the ideal machine, the efficiency is always 100%. But ideal machines don't exist. There's always friction that will rob a system of energy. So efficiency is equal to the output work divided by the input work. So in the problem on the previous page, I had 149.6 joules as my output work, 150 joules as my input work. So when I divide that, I get 0.997. So that machine was 99.7% efficient, which is really, really good. The internal combustion engine, the thing that powers your cars, are only about 40 to 45% efficient. All right, traction. Traction is the friction between a wheel and the surface that it rolls on. Friction always opposes sliding, so we can study a couple cases here, one where the wheel is being powered and one where it's not powered. Okay, so let's talk about the powered wheel. That's on this right here. So here's our wheel. It has a radius r, and there's a torque being applied to it. At the very bottom then, when we study the forces acting on it, we would have a gravitational force. We would also have a normal force. This torque is having an applied force exerted on the ground. Friction opposes sliding. So as this wheel wants to slide, that means that friction must point to the front, which is really counterintuitive if you think about it. So if we were to start studying forces, so if I look at the net force on the y-axis, I have equilibrium. So that tells me that the normal force should equal m times g. If I study the forces on the x-axis, if I were to say that this way is positive and this way is negative, I would have that applied force minus the friction. Now, if I have traction, if I want to push this wheel to its maximum limit, I want to find out the maximum static friction that it can handle. I would need this to be in equilibrium. Because once this force becomes greater than the maximum static friction, we'll lose traction and then do a burnout. All right, so this traction force here, this would be torque divided by radius, because torque is force times lever arm distance, and the lever arm distance is the radius of the wheel, minus static friction times the normal force, that's our formula for friction, equals 0. So, just doing some algebra here, found out that the normal force is mg. So torque equals coefficient of static friction, mgr. So this is the equation then for traction of a wheel. Now the non-powered wheel, that's this one right here. It's being driven, it's being pushed. So let's say it's rotating this way. There's no torque on it, but it's being rotated. So here I would have the gravity force, the normal force, and this time, if the wheel were not to spin, it would slide. So this time, friction goes in the opposite direction. So notice how friction changes its direction depending upon if the wheel is powered or non-powered, which again I think is really incredible. It's really kind of fun to think about. All right, that finishes this this entire unit's worth of notes.